Everyone knows reading out of the book is boring. Have you ever wanted to actually see how electrical energy can be produced by permanent magnets? How electricity can be reverted back into magnetism? Or how electricity can be transferred wirelessly using magnetism? Of course you have. Well, today, I'm gonna show you. First, we'll look at the AC generator. I made the frame of the generator out of this empty pill bottle, but anything with this shape would have worked. The stator windings will be wrapped around it. I suspended a permanent neodymium magnet inside the frame, with this piece of wire acting as the rotor shaft. I wrapped 100 turns of magnet wire around the frame on each side of the rotor shaft. After connecting the meter, with just a few hand turns, you can see that it generates a few hundred millivolts already. Well, that worked. After repositioning, my generator proved very effective. Pay close attention to the meter readings. At medium speed, it hovers around 35 to 40 volts. At higher speed, it was reading in the hundreds of volts. It capped out at 400 volts before exceeding what the meter can read. Next, we'll look at electromagnets. Electromagnets are made by wrapping wire around a ferromagnetic core, generally iron. I made this one using a 16 gauge wire, wrapped about 160 times around a half-inch socket extension. I powered it with a 4.1 volt lithium cell battery. The wire resistance is 0.2 ohms, so the current is just over 20 amps. With this 12 volt power supply I made, it's drawing about 60 amps. These diodes were running a cool 75 degrees Celsius. I figured I should try something heavy. I made another one with about 650 turns on a 3/8 extension with a shorter coil length. With the battery, it's drawing about 290 milliamps, and with this 12 volt power supply, it draws 840 milliamps. This last one I made with 2400 turns, wrapped along a small screwdriver with a much longer coil. Despite having so many turns, they're less dense than if they were in a shorter coil. The wire resistance is 52.4 ohms, so the current is negligible at 12 volts. It makes for a pretty weak magnet. Let's have a look at transformers. I salvaged the wire from the useless magnet to make a second coil on the small magnet. I wrapped them in 2 sets of 150 turns with a center tap. I put 10 volts AC on the side with 650 turns and measured the voltage across the 300 turns on the secondary, which was 1.42 volts. Then I measured each leg of the secondary to the center tap and got 0.73 volts and 0.68 volts respectively, which adds up. The set of turns with less voltage is wrapped entirely on top of the set with more voltage, so it's farther from the core. The magnetic lines of flux are more dense near the core. The low total output of the secondary doesn't reflect the turns ratio because of 2 things: poor efficiency and my ballpark guess of 650 turns on the primary, which I didn't use a marker to count with like the rest of them. Transformers are more efficient when the cores are made of laminated iron sheets and take up more of the magnetic field around the coils, and when the coils are closer together. The coils are more efficient based on the conditions I demonstrated with the electromagnets. And we're going to end it off with motors. Here's a fun fact for you. If you rest a magnet floating in water, it will align with the Earth's magnetic field like a compass. This setup was the easiest method to perform this next experiment. The floating magnet can be imagined as the rotor of a motor. When I introduce an external magnetic force, the floating magnet will align itself with the magnetic field of that force. This external force is like a single stator pole in the field windings of a motor. Flipping the magnet in my hand is the same as changing the polarity in the stator pole. The closer the magnets are together, the stronger they interact. Stronger magnetic fields equate to stronger motor torque. I wrote a program for my Arduino board to change the state of 4 MOSFETs. The output of the MOSFETs is a DC voltage, the polarity of which will change depending on the state of the button. I've set up some LEDs so that you can see the condition of the button, and a DC voltmeter so you can see the voltage. The output voltage is sent to my electromagnet, which influences the floating magnet, or rotor. When I press the button, the voltage changes direction, and the electromagnet changes polarity. This is why in an induction motor, the voltage and current control the torque, and the frequency and the number of poles control the speed. If you're interested, I made a video where I blow some stuff up in slow motion, and I'll be posting soon about building a DC drive and a VFD. I hope you enjoyed. Thanks for watching.